When are we getting our test?
Maybe a week from today. Yeah, what?
I want to know now.
It's a stack this big. And you guys can't know when to stop writing. So that's about what I think I can get. I need another weekend to work.
Yeah.
I asked a question when you asked why is it important for the Earth to be old. Can you elaborate on what answer you expected?
She wants to know, like, why is it important to have a notion or know that the Earth is very old before you could really develop an understanding of evolution, particularly by means of natural selection? That's the question I asked you on Wednesday. Yeah. Why? What's the important? Why is it relevant that the Earth be really old? What if it was only 10,000 years old? Yeah.
Because evolution takes time, and for lineages to diversify and transform, they cannot just spontaneously happen.
Yeah, so if the Earth isn't old, this other stuff can't work, right? There's not enough time. And so if you're dead set on the Earth being really young, you would never come up with those ideas or that mechanism. Maybe you could propose it, but it doesn't make any sense. It can't work that way. So it went hand in hand with understanding that the Earth is really old. And so they figured out it was really old using some things like, remember the geologic time scale that we ended with, which is where we're starting today? People looked at changes in the characteristics of the Earth, the physical nature of the Earth, but most importantly on that, the biological nature of the Earth. And you can do some extrapolations and figure out that the Earth is not just thousands of years old, it's hundreds of thousands to maybe millions or even tens of millions. And once you realize that, then you realize, oh, there is time for these processes to take place. Okay, remember the same thing with uniformitarianism. We're talking about large-scale changes in the physical nature of the Earth's surface using processes that operate today, but they don't change the Earth very much in short amounts of time. You need a lot of time. Okay. They also they knew that the Earth was very old, but they had no notions that it is really as old as it is. Okay, and that's what we're talking about today. We're talking about how do you know that and how do you measure that. Does that help? Yeah, so I want you to link those two things together. Anybody have other questions about stuff from last week? Okay, so when we ended on Wednesday, I showed you this thing that's called the geologic time scale, and it lists all kinds of events that people have learned about the history of the Earth, particularly history of life on Earth. And when there are big marked changes, people draw lines and call different pieces of times, they give them different names. And so we divided up the history of the Earth into pieces of time that we've given different names to that reflect changes and things that have taken place. And those events are relative to each other. Some event happened before something else, other events happen after other things. And so that's when we're talking about relative time. This is older than that, or this is younger than that. That's relative time. It's relative to something else. But then there was a column on that table that is actually fairly new. It comes from the 20th century. And that's absolute time. So there's a thing on there, and it says extinction of the dinosaurs was one of those lines. And so that happened before the first human beings, but it happened after the first fishes that had jaws. That's relative time. But there's a number there in that one column that says 65 million years before the present. How do we get that? How do we get absolute time that we can, where we can assign real numbers in the Earth's to events in the Earth's history? Yeah.
Is it carbon dating?
No, but carbon dating is a kind of something that we use. No, carbon dating does work, but on that geologic time scale of this big, carbon dating is a kind of what's called radiometric dating. And it relies on the radioactive decay of atoms of different characteristics. Carbon dating is one of those, and we'll talk about it today. But carbon dating is only good for, if this is the entire geologic time scale, carbon dating is only good for maybe, you know, that little spot right up there, less than 1/4 of an inch, or even smaller than that at the top. So there are different kinds of radiometric dating, and that's the first technique that we'll talk about of how people put absolute dates on events. So carbon dating that he brought up is a kind of what's called radiometric dating. And it depends upon the fact that there are radioactive isotopes of elements that exist on Earth. So different elements have different numbers of what? Protons, yeah. So depending on how many protons you have, that's what dictates what element you are. Sometimes those elements come in different forms because they vary in the number of neutrons that they have, and those are different isotopes. There are isotopes of some elements that change. They radioactively decay. They throw off subatomic particles, or subatomic particles are converted from one thing into another. If a proton is converted from a proton to a neutron, you have something different. It's not the same element, and you can measure its existence. You can count how many, say, atoms of one element are in a substance and how many atoms of another element. Or, since they are different, you can count how many isotopes of a given element you have in a substance and how many isotopes of the other different isotopes you have of the same element in something. The key here is that radioactive isotopes of different elements decay, that is, they change into something else at a known, constant, and measurable rate. Anytime you have something that changes at a known, constant, and measurable rate, you can use it as a what? Some of you have them on your wrist.
Watch.
Yeah. So your watch, you can use that to time things. Why? Because it changes at a known, constant, measurable rate. Either little hand, I don't know if you guys still have watches with little hands that go around. Those things move at a known, constant, measurable rate, or those numbers change at a known, constant, measurable rate. So anything that does that, you can use it as a clock to measure time. In the case of radioactive isotopes, you can look for them in materials like rocks, and you can use the amount of radioactive isotopes of different forms to see how long this rock has, say, been in existence. The trick, though, is just like with a stopwatch, that you know you can run a stopwatch and see that it's timing something, but to know how old something, you have to know what. It's like timing a foot race. You have a stopwatch and it's running, but there's a real important thing that you have to do right. Yeah, you have to know when it starts. When do I start the clock? So we'll see we have various means by which we have these things in nature that vary at a known, constant, measurable rate. So they're always ticking. They're like watches that are always ticking, but we need to know when they start, when something starts, because that's what we're interested in. If it's a foot race, we're interested in how long it takes somebody to go from the start of the race to the end of the race. And so we have to know that. And so we'll see some fairly ingenious ways that people have realized that you can tell when certain clocks tick. Okay? So one of these is using radioactive isotopes, and they decay again at a known, constant, measurable rate. And this rate that we measure in these radioactive isotopes is called a half-life. So a half-life is a rate of decay or a rate of change. So when we're talking about half-lives of radioactive isotopes, that's the time that it takes for, in years, minutes, seconds, whatever, it's how much time it takes for half of what you have to turn into something else. So if you have 100 units of radioactive isotope Q, how long does it take for half of that to become whatever this thing degrades into? That's its half-life. And then it takes another half-life for the next half of it to disappear. That's the term or the piece of time that we use to measure the rate of radioactive decay. And again, these things are measurable, and it doesn't matter about the temperature you have them in. You can make them really cold or really hot. They still degrade at the same rate. You can put them in high pressure. You can put them in vacuums. They always change at the same rate. But different isotopes or different elements that are radioactive, they decay at different rates. They have different half-lives. Some things decay very slowly, so that means their half-lives are what? If an isotope changes into something else very slowly, does it have a big half-life or a short half-life? Big half-life. That means it takes longer for half of it to go away. Okay? So there are some isotopes like potassium 40 that exist in nature. Potassium is a very common element in the surface of the Earth. It's something like almost 2.5% by mass. It exists in rocks. Potassium exists in different forms. One form that it exists in is potassium 40. On the periodic table, potassium is number 19, so that means it has 19 protons and 21 neutrons. That's one form that potassium exists in. This is a form, though, this isotope of potassium is a form that degrades. It turns into something else over time. So there are other subatomic particles like beta particles that are always being produced and rained down upon the Earth. When beta particles hit potassium 40, it ends up becoming one of two things. It either becomes argon 40 or calcium 40. What happens here is we convert one of the neutrons of potassium to a proton and get argon 40. An important thing though, this and this are different things. You can measure, they have different, if they're different elements, they have different characteristics. You can measure how much of this is in a rock. You can measure how much of this is in a rock. You can measure how much of this is in a rock. Also, we know that for however many units of potassium 40 turn into these things, about 12% become this, and about 88% become this. Okay, so this is always taking place. Potassium 40 exists. It's always turning into argon 40 and calcium 40. And it's turning into these two things at a known constant measurable rate, and the half-life of potassium 40 is 1.3 billion years. So if you have 12 atoms of potassium 40, how long do you have to wait to have only 6 in your hand? You got to wait 1.3 billion years. If you wait another 1.3 billion years, how many do you have in your hand? You only have 3. But it's not magic. They don't disappear. They go somewhere. Okay, that's a cool thing about chemistry. Stuff doesn't come and go in chemistry. Everything's accounted for. Those atoms become something else. Some of them become this, and some of them become this. A cool thing, though, about this is a gas. And when rocks get liquefied, they get so hot that they become liquid, argon gas leaves and dissipates. Okay? There's still this in rocks. There's still this stuff in rocks, but this disappears. Okay? Now you go out and you find a rock and you collect it. how can you tell how old it is? And when we're talking about rocks and we're interested in how old they are, we're really asking, when was the last time it was a liquid material? Okay? So, if I have this rock in my hand, and it has a lot of argon-40 in it, has it been around a long time, or is it a brand new rock? It's been around a long time. The only way that you get argon-40 in rocks is from the conversion of potassium-40 to argon-40. So what could you say about a rock, and you measure it, and there is virtually no argon-40 in it? What could you say about that? It's what? No, the opposite. No, it's real new, right? Because that means it's very recently gone from a liquid, where all the argon-40 leaves, to a solid. Now it's solid, just picture it, the gas that's being generated in there can't escape. Where would you find rocks that would have that characteristic? Almost no argon-40 in them. Yeah, exactly. Go to the most southeastern island of Hawaii, and there's rocks being made brand new today. Okay, those things they don't have argon-40. Okay, you go to places where rocks have been around for a while, they have a lot in them. So what we're doing is it's like a clock that does this. At day 0, there's no argon-40, but there's potassium-40. And this is always taking place. Okay? So the amount of potassium-40 is always going down, but it's not disappearing, it's turning into something else, argon-40. Okay? And eventually, you're going to have a lot of argon-40 and very little potassium-40. That's how that's the ticking clock, that's the thing that's changing at a known constant measurable rate that we use to figure out how old rocks are, particularly very old rocks. So this is something that you would use to put dates on rocks that are old. So you can put dates on rocks that are over 2 billion years old with an accuracy of plus or minus 1%. Okay? So this works for very old things. Other isotopes you would use for newer things. If you're looking at some rocks that aren't very old, would you use isotopes that have half-lives that are very long or very short? Very short. And when we get to carbon-14, which is a different situation, we'll see that it has a relatively very short half-life. Okay, so we use this for very old things. Now, this is the way it really works out in truth. Potassium becomes two different things, but we know the proportions, and it makes the math a little more complicated because we have to multiply our breakdown products always by 0.12. But let's make a real easy situation over here. What if we have isotope X and it becomes isotope Y, and it has let's say a half-life is also 1.3 billion years. And Y behaves like argon. In brand new rocks, it's not there. The only way it gets into rocks is from the degradation of X into Y. So let's say at day 1, in a particular rock, we have 500 parts of X and 0 of Y. If we wait 1.3 billion years, how much X do we have left? How much, I'm going to leave this, looks like I'm minus. How much Y will we have? Right, so every one of those is turned into something else. If you wait another 1.3 billion years, how much X do you have? 125. How much Y do you have? What? Yeah. These things don't go anywhere. They're still there. You just generate some new ones, then we got 375 Y's. If you wait another 1.3 billion years, we got something like what, 67? And what's this going to be? 432? How am I doing? I didn't write this down in my example. We're just making this up as we go along. But that's all we've done all semester long anyways. Oh, 433. That's pretty close. Okay? So again, this number goes down, this number goes up. In reality, what you do is you go out and you find something, take it back to your lab, and you measure how much of this is there, how much of this is there, and then you've got to figure out what you started with. How do you, if this is what you have in your sample, how do you figure out what you started with? Well, these x's used to be, or have always been, what? X's. These y's all used to be what? X's. So you add those two numbers together, you get this. If for some strange reason you should ever have to do one of these things on an exam, what you might do is, here's your sample, add the numbers together to figure out what you start with, and then cut it in half until you get to what your sample is. And then figure out, how many times did I have to cut in half what I started with to get to my sample? How many times did we have to cut this in half? 3 times. Every time you cut it in half, how long did that take? 1.3 billion years. How old is that?
3.9.
Yeah. That sample, that rock, was last liquid 3.9 billion years ago. Okay? How often do you think you go out and you collect a rock sample and it turns out to end up exactly on a half-life? Like this is exactly 3. No, it's probably not very often. But you can extrapolate, interpolate between numbers, or in reality, you just build a formula, right? And it's it's a decay. There's one on your, on the images that are on your Moodle, on the Moodle site. But this is like K40 or X. It goes like this, right? And the other one is going to go like this. So as this goes down, this one goes up, but it decays in this kind of fashion. It's like you keep cutting it in half. If you brought a cake to a party and you want to share it, so you keep cutting the pieces in half, how many times can you cut it in half? Really an infinite number, right? Because every time you cut something in half, you always have what left over? You always got a half left over that you could cut in half. Okay? Well, what about in practice, though? Yeah, pretty soon you get to a piece of cake that nobody wants because it's way too small. Or eventually here you'll run out. Okay? This has such a huge half-life that we don't run out of these things. We'll see, though, that limits on carbon-14, though, you get to a point where there's so little of what you started with left that you can't measure it anymore. Even in reality, there may be something there that's too little to be measurable. So that's why we use different isotopes for different time lengths. So really old stuff on Earth, this is one of the techniques that, that people use. Okay? So now we can go to different places on the Earth and measure the ages of the rocks and find out when were they last liquid. So anybody know what the oldest rocks that people have found on the surface of the Earth are? Hundreds of years? Thousands of years? Hundreds of millions? Or billions? Or hundreds of billions? How many?
4.
Yeah, like a little over 4. So like I wrote down some of the oldest rocks that people have found on Earth. So this is on the surface of the earth. So people have found rocks that are 4.28 billion years old. That's the last time they were liquid. So the last time they were liquid, in this case, was around the formation of the earth, when it went from a liquid to a solid. There's some other, and so those are places in Quebec, Canada. There's some 4.03 billion year old rocks in Western Canada, and there's some 4.38 billion year old rocks in Western Australia. From that, we conclude that how old is Earth? A little older than that, and we figure it's about 4.6 billion years old. Human beings go to the moon in what year? 1969. Oh, extra gold. He gets a gold star for that. You know what that does for your grade? Nothing, but he's got a gold star, yeah. 1969, they bring rocks back. How old are they? They're 4.6 billion years, okay? There are little pieces of our solar system that fall onto the Earth, okay? The Earth is getting bigger every day. In the past, it got bigger really fast. Today, it gets bigger at a really slow rate because the pieces it's gathering by gravity are pretty small. But sometimes those things don't burn up before they hit the ground, and you can go and pick them up with your hands. How old are those things? They're the same age. So what does that tell us about our solar system? It's about 4.6 billion years old. So that's how long we've had a planet. And again, you don't go from no planet to planet in a day. We'll talk about this later in the semester, but planets coalesce by condensation of material around them. They grab pieces around them. Sometimes they grab big pieces. Lots of this, what they grab are small pieces, and eventually they just get bigger and bigger and bigger. As I said, our planet is still getting bigger today, but it's only grabbing little pieces. That's all really we have left in the area to grab and make part of the Earth, but it gets bigger by thousands and thousands of tons every year. But those pieces of the solar system were last liquid 4.6 billion years ago. So that's how old our solar system is, okay? So we can go out and put dates on rocks in different parts of the Earth. Sometimes rocks are real young, okay? Like we said, if we went to some volcanoes, those rocks are brand new. They just went from a liquid to a solid relatively recently, and so they're very young. Others are hundreds of millions of years old. You can go up to the San Gabriel Mountains and pull rocks off of the wall there. They're over a billion and a half years old, and they're right there in front of your face. You can pull them off and look at them. They've been solid for that long. That's a long period of time, okay? So that just gets us one of those things on our geologic time scale, how old the Earth is, say 4.67 billion years old. How about those other things, those other large events in the history of life on Earth? How do we put dates on those things? Well, we use the same techniques, but we measure. Our samples are different things. So we go out, or people go out, and we look. You search for what are those things that are inside strata of sedimentary rocks? Yeah, so they're fossils. So here's a fossil of something right here, and we want to know how old that is. If this was your job and you went and found this fossil, it's a rabbit. Okay, you can recognize it as a rabbit. So what do? You want to go out and find out how old that is. What are you going to do? Anybody got any idea what they're going to do? What would you collect? What would you bring back?
The rocks surrounding it?
The rocks surrounding it, okay? So you go and you take some of these rocks right here. So there's just little pieces of rocks right next to where the fossil is. That makes sense, right? So you bring these back home to your lab, you run analyses on them, and you find out that they are 900 million years old. Are you happy with that answer? Your technique worked, everything is good. You did everything right. And your answer is 900 million years. Now, we haven't talked a lot about some of the time frames, but some of you have a problem with it. You have a problem with that? You think it's too young or too old?
I don't know, it depends on the rabbit.
No, it doesn't depend on the rabbit. Yeah, I can tell you this is way too old. Okay? You gotta go back to get multicellular organisms. They don't even show up until late 500 million years. So this is hundreds of millions of years before, okay, we also independently have this magic box that we can look in. And we know that unicellular organisms don't show up until a little bit younger than 600 million years old. How do you find a fossil rabbit in 900 million year old rocks? And I'm telling you, you did everything right.
Gophers.
No. Although gophers do move fossils around because they dig up stuff from deep, they bring them to the surface, and stuff from the surface gets moved around. So in real life paleontology, you got to be careful and watch, know what you're doing, because that does happen. That's not what happened here. Yeah.
Maybe earthquakes, like kind of shakes the strata.
No. No. What did we just answer by dating these rocks here? These are sedimentary rocks, right?
Formation of the rock.
Yeah, all you did was determine the last time the sand grains that make up this sedimentary rock were liquid. Did the last time these rocks were liquid, was that the same time that this rabbit got buried there? Where did those sand grains come from in this sedimentary rock? They came from up in the mountains, because the mountains are eroding away and making sand that goes, all that sand at the beach, when you go to Will Rogers Beach for a nice summer day, you're walking around in the sand, all that sand came from up in the mountains. But did it get melted? No, those are hard rocks that are now little pieces of big rocks. They never melted, okay? So all you figured out was the last time the sand grains in that sandstone were liquid. What does that have to do with the age of the rabbit? Only one thing, that it's older than the age of the rabbit. That's all it tells you. But as far as what we're interested in, when that rabbit existed, it doesn't tell you anything. So now we're back to the drawing board. What are we going to do? Yeah.
We use the layers, different layers, and age each layer.
Okay, so we could do that, and the numbers jump all around. This is 900, this is 1.2 billion years, this is 100 million years. The numbers are all over the place. All that tells you is the rocks that make up the sandstone are coming from different sources, maybe even different rivers as they change course. So that doesn't help at all. It actually makes it more, it's just messy. We're still not doing something right, yeah. This is way too old for that. There's no carbon. We can't do carbon dating on this thing because there's nothing. This is a rock. This is an impression of rabbit skeleton in sandstone. What we want to do is what? We want to find some rocks really close to that area that were brand new at that time. What kind of rocks are that? It's not even a good sentence. You guys said it already. What are brand new rocks? Where's a good place to look for brand new rocks?
Hawaii?
Volcanic rock.
Yeah, volcanic rocks. What do volcanoes do? Some of them spew out molten rocks that run down the sides. Some of them come up from underground and spread out sideways. Lots of volcanoes also do what? Erupt. And what happens to the rocks that are brand new then? They go a long ways. And they go up in the atmosphere, like when Mount St. Helens erupted in 1980. I mean, it sends rock. Now, it doesn't. These kinds of rocks come down pretty fast. These kind of rocks get up in the atmosphere, and they get traveled on winds. They spread a long ways, and then they come down in the form of what? Volcanic ash. Okay. So what you do when you're putting dates on fossils is you look for volcanic ash layers. What do you know about those volcanic ash layers? When that got laid down, how old was that rock? Brand new. So, this is brand new rock. Here, It's brand new rock here. So when you go out and collect your samples of rocks to put dates on fossils, you don't bring back the rocks that the fossils are in. You look around for volcanic ash layers. Now, do volcanoes explode every week? No. Do they explode every year? No. But they happen frequently enough that these volcanic ash layers are not that uncommon. That's what you bring home to your lab. That's what you put a date on. And then you find out that this ash layer right here is 80 million years old. And this one here is, what number? Bigger than 80 or less than 80? Probably less than 80. 72 million years old. How old is the rabbit fossil? When was that rabbit walking around? You at least know that, don't you? The only way for this thing to get here is that had to be there before this happened. So it's older than 72, but it happened after this volcanic ash layer was laid down at 80, so you at least know it's younger than 80 and older than 72. So all of these dates on fossils, this is what you do. You don't use the rock, the sedimentary rock. That thing didn't become liquid when that sedimentary rock was laid down in that event that buried that dead rabbit, but that's what we're interested in. So we have to look around for brand new rocks as close to that event as possible. And that's what you put dates on, and that's what you use to date fossils. Okay? Does that make sense? Intuitively how it works? Okay? And then we use these techniques here to put dates on things. Of course, we probably wouldn't use the potassium-40 technique for this. Why? It's pretty young. So we may use something else like a uranium isotope. But there are multiple isotopes that have different rates of decay, different half-lives, and stuff that's really old. We use things with long half-lives, and things that aren't so old, we use things with relatively new half-lives. Okay, any questions on that? Okay, so some things we use different isotopes to put dates on them that have different compositions. So, what was you told me your name before. What's
that?
your first name?
Harag.
What?
Harag.
Harag brought up carbon-14 dating, and yeah, like the gentleman in the back, I don't know if he's really a gentleman or not, but he's back there. He said, you know, things that have carbon in them, you can use a carbon dating technique that uses a different isotope. So we're not dealing with stuff typically that's buried deep in strata. We're dealing with things that aren't that old, because after a while the carbon organic materials degrades into something else. But carbon comes in different forms. So carbon is what number on the periodic table?
12.
You have to see the tomb you've missed already. Yeah, it's number 6. So it has how many protons? 6. And most of carbon is carbon-12.
Yeah,
It
that's what I meant.
has, that's not what you said. So most of it has 6 protons and 6 neutrons. But some of them have 7 neutrons, so there's carbon-13. And then nitrogen, which is very common in our atmosphere. So you wave your hand around in here, you can feel this room is not empty. It's full of stuff, this air in our atmosphere. And something like 70-some% of it is nitrogen. And that's just one spot away on the periodic table. Well, nitrogen's always being bombarded by cosmic rays, and that changes some of those nitrogens into carbons that have 6 protons and 8 neutrons, and so that's carbon-14. Okay, so that's always being generated, but it's always degrading. It's always it's a radioactive isotope. It changes over time at a known constant measurable rate and reverts back to nitrogen and free electrons. Carbon-14 has a half-life that's fairly short. It's 5,730 years. So if you have a handful of carbon-14 and you wait 5,730 years, you only have half a handful of carbon-14, and the rest of it has become nitrogen and free electrons in the atmosphere. We can use this to put dates on things that are made of organic material, because carbon-14 is out there in the atmosphere, and it exists, I think it's something like one out of every 10 to the 12 carbons is a carbon-14. They're not a lot, but they are a known amount, and it's measurable. Okay? Actually, from the 1950s to the early 60s, the amount of carbon-14 in the atmosphere doubled. Got any idea why?
Gasoline.
No.
Nuclear bomb?
Yes, yeah, because of nuclear testing. Okay, those high energy explosions changed a significant amount of nitrogen into carbon-14. The amount has gone up significantly, but we know that, and so that works into our equations. And so there's carbon-14 in a known amount. 1 out of every 10 to the 12 carbons is a carbon-14 in the atmosphere. What happens to carbons? Just say single atoms of carbons. What's one thing that happens to them in the atmosphere? They get oxidized, okay, and become another molecule of CO2, okay? So one of the things that becomes of carbon is CO2. Well, some CO2s in the atmosphere, instead of being made of a carbon-12 or a carbon-13, they're made of a carbon-14. So those have different characteristics. So how many of the CO2 molecules in the atmosphere are carbon-14s? Well, this same proportion here. What happens to CO2s in the atmosphere? What's one thing that happens to them?
They react with ozone?
There are organisms on Earth that take CO2s and they take waters, and to build big molecules from small molecules requires energy. And so they stick waters and carbon, CO2s, together, and they use energy from the sun to make bigger molecules. That process is called what? Okay, you redeemed yourself a little. They build big molecules. Why do they? For what purpose do these animals build these big molecules out of small molecules?
To break it down.
Sugar.
Yeah, they take them apart. Well, I just said it took energy to build big molecules from small molecules. A lot of that energy is stored in those bonds, and if you take them apart very carefully in these processes we call metabolism, you can release that energy in a form that is used to build other molecules, like ATP from ADP and phosphate groups, that you're going to immediately take apart and release energy in another form that you can use to do work. But they also use those to build their bodies. Okay? So a living plant, how much of it is made out of carbon-14? 1 out of every 10 to the 12 carbons in its body is a carbon-14. It's in equilibrium with the environment. Okay? Now you eat that plant. Okay? And you build your body using those plants, or you eat other animals that ate plants. Okay? What is your proportion of carbon-14s? The same thing. So all living things are in equilibrium with the atmosphere. At 1 out of every 10 to the 12 of their carbons is carbon-14. So you're in equilibrium. What happens when you die? So you're losing. Some of your carbon-14s are breaking down by radioactive decay, but you're always getting new ones. What happens when you die? Well, what happens to the carbon-14s that you're made of? They decay. Do you get any new ones though? No, because you're no longer consuming things or doing photosynthesis. So you're at a known amount of carbon-14s as long as you're alive. When you die, it starts going down, right? And so what you do is you get objects that are organic, like what? What are some things that you could use a carbon-14 technique on to put dates on? Turkey bones. Yeah, okay. So those are made out of what? Organic material. They're made out of carbons. There's carbons in there. Some of them are carbon-14s. Some of them are carbon-12s. When that turkey was alive, it had that proportion. The longer it's dead, the less of that it has. And people, what you use is a mass spectrometer to measure how much of those different isotopes there are. What's one of the differences in what different characteristic would a carbon-14 atom have versus a carbon-12 atom? It has 2 more neutrons, but that means it's also what? Those neutrons have mass.
Heavier.
And they are heavier, right? So a mass spectrometer, it's like taking a big bucket of tennis balls, and this machine picks up those tennis balls, these atoms that you give it, and it throws it. Okay? If you just keep handing me tennis balls, and I throw them with the same force, they're going to keep landing in the same spot, right? What if you hand me a tennis ball that's filled with sand? It's not going to go as far. That's how this instrument works. It throws these atoms out there. The lighter they are, the farther they go. The heavier they are, the less farther they go. But the point is, you can count them. So I can take these to a turkey bone sample back to my lab, and I can count per unit piece or per unit mass or whatever standard amount that I use, and I can see how many carbon-12s to how many carbon-14s. If there are the amount of carbon-14s are 1 for every 10 to the 12 carbons, how long is that? I just got it. I just ate it. It hasn't been dead for a long time. If that turkey was eaten by somebody 5,730 years ago, it would have 0.5 over 10 to the 12. Does that make sense? That's how the carbon-14 techniques, and you use it on turkey bones. Can you use it on paper? Sure. People write stuff down on paper, and you could, if they don't, in the old days, they didn't used to write dates on stuff. They just wrote things. They often wouldn't even put their name. In a new book today, you open it up, and within a page, it has the publisher there, it has the copyright date, it has the author, it's all clear. They didn't used to do that in the past. So how do you know how old something is? You can date the paper or the papyrus or the wood that somebody wrote on. Does that tell you when they wrote on it? What does it tell you? It literally tells you when that plant material died that gave rise to that paper or that wood. But that's probably pretty close to when? The time that somebody used it to write on, yeah. So you can dig up mummies in Chile and Peru or Egypt, and they have clothes on that are made out of what? Plant material or animal material, or their own desiccated muscles and bones. Those are the kind of things that you use to date using carbon-14. Or you're digging in some archaeological dig and you find old fireplaces, charcoal and stuff like that. That's all the same kind of stuff that you can use. It's those kind of things that you use the carbon-14 technique. But after a certain amount of time, this only works up to about 60,000 years. When you get something that's been dead for over 60,000 years, there's so little carbon-14 left that you really can't measure it with any degree of accuracy. And so even though you may have organic material, that technique doesn't work anymore. Okay? So you go out to a local stream and you find a living snail and you take its shell and you run your carbon-14 technique on it, and it says that it's 20,000 years old. Your technique is good, your instruments are good. That shell on that snail is 20,000 years old. What's up with that? Is that possible? And yet it's true. We're talking about, you gotta, remember he mentioned gophers, okay? You gotta understand what's going on. How could a living snail have a shell that says it's 20,000 years old, and yet it's still living and crawling around there? What is its shell made out of? Calcium carbonate. Where did it get the calcium carbonate that it used to build its shell? From the water. Where did the water get the calcium carbonate? From rocks, okay? So they're using building materials that really are old, but they're using those building materials to build their new shells. So that's not a good thing to use to find out how old that snail is. You gotta understand what you're doing, you gotta understand what you're measuring. It's the same thing when we were looking at those strata. You can go and put dates on the sedimentary rock, but it doesn't tell you anything about what you were interested in. So we gotta look for volcanic ash layers. You know, as close to that real fossil as you can get. Can you think of some other things that people use to put dates on stuff in the past? How about, oh, your tables aren't fake wood, they're fake rock. That's no good. Why would it be great if your tables were made of fake wood? What would you see on them?
Rings.
Yeah. So what do you know about the growth rings on trees?
Every year.
Shows you how old they are.
Yeah, particularly in higher latitudes, when you have really marked seasons, and during the cold winter months in the fall, growing conditions aren't that great, they grow very slowly. So trees put on growth at the tip, at the meristems, but also the cambium, the side. Trees get taller and they get wider. And then during the poor time of the year, they grow slowly and make very dense wood. And then in the spring and summer, when there's lots of water, they grow quickly and make fairly, really less dense wood. And you can look at a piece of wood and you can see these annual growth rings. Okay? Oh, we've got another ticking clock. It's something that adds something at a known constant measurable rate. It adds a growth ring every year. Okay? Are all the growth rings the same? No. Sometimes the growth rings are really close together. Sometimes the growth rings are very far apart. That's related to what? Yeah, good years and bad years. So we've had a drought for so long, if you cut down our local trees, and go ahead, they're all dead anyways, and look at the outside growth rings, they're very close together. We've had multiple really poor growing years. If you go back a few decades, you can hit some good years. And the growth rings are far apart, and they make a pattern. Okay, like that. So here is a bunch of annual growth rings for about 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 15, 16, 17, 18, 19 years. This is a pattern, and this is actually a distinctive pattern that you would only find during this time. So you go get another tree. Ideally, you would use the same kind of tree. Why is it good for comparison to use the same kind of tree? Well, different trees grow at different rates. So redwood trees grow really fast. You go buy redwood at Lowe's or Home Depot, some of those growth rings are that far apart, okay? You go get some hardwood like walnut, and the growth rings, they're pretty close together. But the pattern is the same. The relative distances are the same. And then from the same place, you should have the same kind of pattern. So what we can do with a piece of wood that's alive today, we can say that this is 2016, and this is 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 2000, 1999. This is 1998. What people have built are libraries of these patterns by going out and getting pieces of wood from trees of known age. If they're living today, you know that the outer growth ring is today. And you build these libraries with big trees going way back in time. So we'll say we built one way back in time here. And then you get other pieces of wood from trees that have been dead for a long time. And what you do is you get the same pattern of lines and you match it up. You could do it with your eyes. Nowadays people use computers to match it up. So if you found a piece of wood that had this pattern, like that, this piece overlaps with this piece, and so now we can go further back in time. So this is also 1998, and then this is 97, 6, 5, 4, 3, 2, 1, 1990, 1989, 1988. And so people have done this, and we have patterns that go back hundreds and hundreds of years, even to thousands of years. Some of our individual trees, I brought up redwoods, can live for way over 1,000 years. So people build a library of these patterns, and then you can go out and collect something or find a sample of wood, and essentially what you do is you take it and you hold it up to this pattern here, and you find out where your sample overlaps. So you may have some piece of wood that you, in your archaeological excavation, you found some old wooden dwelling. You could take that piece of wood and you see that it matches this part right in here, okay? So what does that tell you about the age of that dwelling? Well, the only thing that it tells you is that the wood that somebody used to build it, that piece was at least alive during this piece of time, which would be around the year 2000, okay? So that means that that thing was older, and it tells you that this dwelling was built and people lived in it in this time, not in this time back here. Does that make sense? It's other pieces of information that you can use to answer your questions and figure out how old things are. This is something that's called, what does dendro mean? Tree. Yes, dendritic. You know, like a dendritic pattern of streams. It's literally mean it looks like a tree, because that's the branching pattern. Or dendritic nerves, because that's how nerves, you know, they go and they branch and they branch. They're like trees. So dendro is tree. This is called dendrochronology. This has to do with time, the measurement of time using trees. Yeah.
Did these tree timelines exist like universally, or were they only like regional?
People build them regionally. So they got, and what they do is you don't keep big pieces of wood. Even in living trees, what you can do is make cores. It's like drilling into the living tree, but it's a hollow drill, and you can pull out a core that looks like a straw, but it's a solid piece of wood, and you lay it down on a table, and you see those very clear marks. And so those are the actual objects that you would keep in say a dendrochronology library. But then you would end up converting it into digital information like this, so that you don't get a wood, you're running around actually comparing it. You know, you build this pattern. But the thing is, you build it with other pieces where they overlap. You can push these libraries of information way back in time, and then you use them to answer questions about the age of something. So what else could you do? We have this piece of wood here in this that we took from this home. We used dendrochronology. What other technique could you use to put a date on that? Yeah, couldn't you use the carbon-14 technique? Sure you could. Why? It's a piece of wood. It's organic matter. And that date will tell you when. It'll tell you when that tree died that gave rise to that piece of lumber that was used to build that house. Okay? That at least happened before somebody built that house. Make sense? Okay? So radiometric dating is one thing we can use to put dates on things. Dendrochronology is another thing. There are some other biological entities that in many cases change at a known constant measurable rate. What are those? Molecules, like genetic material. Some parts of our genomes, what are those changes that happen in genetic material? Mutations, yeah. So particularly in non-coding regions of our DNA, mutations are taking place. In different kinds of organisms, different organisms have different mutation rates, but in some regions of the genome, those mutations take place at a relatively constant rate. So we could use the change in genetic material as a what? As a clock. Okay? So that's what's called a molecular clock. We've already used a molecular clock in this class already. Can anybody remember what question we answered by using a molecular clock? Exactly, yeah, how long has HIV been in people? So how did we answer that question? We looked at HIV we have today, we went back in time and looked at older samples that are different, and figured out how different in known pieces of time, how different are they, and then we figured out a rate, X amount of change per 10 years. And then we took that rate and we pointed back in time to see where HIV would have been all the same. It came from the common ancestor, and we found out that that was around the 1940s plus or minus 10 years. Okay? But that is based on the assumption that that virus changes not at just a measurable rate, which we can measure, but a constant rate. If it actually increases the rate of change, then that gives you a faster time than is the truth, or a slower time if the rate of change decreases over time. But what we do is we build a phylogeny. We use phylogenies for solving lots of things. So let's say we have a real simple phylogeny that goes like this, and we have 3 taxa, A, B, and C. And let's say that independently we know that this divergence event, so this is a known event. Using other means, we know that this diverged from these two things at 15 million years ago. How might you know that? Well, we could use the fossil record. We could use radiometric dating to put dates on fossils, or perhaps we know the date of some geologic event. So there were lots of marine organisms that lived in between North America and South America for a long time, and lots of those were wide-ranging species. And then 3 to 5 million years ago, we get Central America. Now you've got what? Marine organisms that are on both sides of Central America, and they diverge and become their own things. They used to be one thing, now they're separated from each other, and they become different things. But we can measure when Central America came into being, and the Pacific Ocean got separated from the Caribbean, and so that's one way that we can put a date on this divergence. If we know when those two lineages got geographically separated and went and did their own thing. So here's a known divergence event. And then we go and measure genetic differences between this, this, and this. And then we see that A versus C they're about 60% different. So we pick a piece of the genome and we compare the A's, G's, C's, and T's, and we see that this is, the region from A is 60% different from C. How much would you, if that's true, how much would you expect B to be from C? Any ideas? Really different or the same? Yeah, it should be about the same. Why? Well, B has been separate from C the same amount of time that A has been separate from C. So if the mutation rate is even close to being similar, they should be about the same differences. Then we go, and what we're interested in is we want to know, when did this happen? Well, we can do that by looking at the difference between this and this. And so if we look and we see that A versus B is 20% different, when did this happen? So what's the proportion of this difference to this difference? This is 1/3 of this, right? If in 15 million years we got a 60% difference, how many millions of years should we expect it to take to get a 20% difference? Yeah, a third. This is a third of that, so it should only take about a third of the time. So then our answer here, using a molecular clock, this should be about 5 million years. So all of this is a molecular clock. Okay? So if you develop a molecular clock for a species of earthworm, is it a good idea to apply that to some genus of palm trees? Yes or no? I wouldn't. Why? Well, we know from looking at mutation rates and change, background rates of change in genetics, it varies from organism to organism. So if you build a molecular clock, we learn it's pretty good to apply, it works best to apply that to the same kinds of organisms or very close relatives. You're making some assumptions. What are some of the assumptions that you're making? That the rate of change is fixed. Yeah. Okay, that's not often the case. In doing this, what might alert you to the fact that the piece of genetic material that we used here has variable mutation rates? Well, what if these two values were really different? So even though we know it's the same amount of time from here to here, and here to here, and here to here, if we got different rates showing up here versus here, that might indicate that those pieces of DNA change at different rates, and I would throw it out and go look for other pieces of DNA that may have very similar rates of change here. Again, this is just another way of putting dates on events that happened in the past. And the best thing to do is if you can use multiple techniques, use multiple isotopes, use multiple different techniques to put dates on the same things, and if you start getting the very similar numbers, what does that tell you? You're probably right, and that's the right dates for things. If you're getting wildly different numbers, you got to go back to the drawing board and figure out why. Is it your instrumentation? Is it your sampling protocol? Or is it the assumptions that you're using to in your the techniques that you're using? Okay. Anybody got questions on putting dates on stuff? And it's using all of those techniques in concert with each other that we get that column in the geologic time scale that has absolute numbers on it. And that's not that old. It wasn't that long ago. Particularly, it hasn't been that long that we knew enough about radioactivity. That's a relatively new understanding about our world, yeah.
Is this called genetic dating or molecular clock?
I call it molecular clock, but I think genetic dating, it sounds like it's the same thing. It might be two terms for the same thing. If you called it genetic dating, I think I would kind of get it. Yeah. Sounds like some cheap way of picking up somebody for the weekend. Genetic dating, yeah. Sign up here. That's the cleanest joke I can think of associated with it. Okay. Let me just look at, I just have 3 pictures to show you. That. The geologic time scale that's in your book is kind of lame, but there is one there. So I would refer to this one that you now have that I have on the Google site. And do you have to learn all these numbers and all these events? Yes. Okay, he said it, not me. No, don't do that. But it's interesting to look at some of these things and look at these time periods and get kind of a feel for the history of life on Earth. When we talk about people, this is us way up here, okay? Our species, this is 1.8 billion years ago for things that we would classify in the same genus. We don't get Homo sapiens until way up there near the top of the line, only about 200,000 years ago. But this is an interesting thing to be somewhat familiar with. And if you're a paleontologist, these are the kinds of words that you use and throw around to talk about different periods of time. I also included a diagram here. That shows what I was drawing on the board, and here is our radioactive isotope that decays, but it doesn't go away, it turns into something else, and these are the breakdown products, or in this case they call them the daughter atoms. These give rise to these, so as these go down, these go up. And you can build formulas that represent these curves, and then all you do is plug in the numbers and solve for the missing value to find the dates of things. And then here's a nice picture of a tree stump from the San Bernardino Mountains, showing you very clearly these annual growth rings. They make really nice patterns, and it's these growth rings that give wood that's cut with different perspectives to these growth rings, the nice patterns that wood has. So I think that's the end of those pictures for paleontology and dating. When we come back on Wednesday, we'll talk about comparative anatomy. All right?